Hi there. So here we are. We are going to start solving our logarithmic equations. So solving these logarithmic equations is going to follow like a pretty similar process to solving any kind of equation. You obviously want to isolate your variable, simplify anything that you can, and solve. So that's exactly what we're going to do here. Remember, we're going to incorporate our quotient property and our product property and our power property, those properties of logarithms. And here we go. So in example 1, we have log base 3 of x minus 4, and that's going to equal 2 times the log base 3 of 4 minus the log base 3 of 2. And something that I noticed right off the get-go is that all three of those terms have the same base. They're all log base 3, which is wonderful for us because that means we can condense these terms very easily. Another thing that I noticed is that on the right-hand side, I see 2 log base 3 of 4. So I'm going to apply that power property. So instead of 2 times log base 3 of 4, I can rewrite that as the log base 3 of 4 squared. And we know that 4 squared is 16. So I can rewrite this as log base 3 of x minus 4 equals log base 3 of 16 minus log base 3 of 2. Again, on the right-hand side, I notice that I'm subtracting 2 logs with the same base. So that's going to be using the quotient property. So when I subtract 2 logs with the same base, I can divide the arguments. So that's going to give me log base 3 of x minus 4 equals log base 3 of 8, because 16 divided by 2 is 8. Now, because the logs have the same base, it says if every term is a log with the same base, set the arguments equal to each other. Okay, that's really going to help us here because now all we have is x minus 4 equals 8. And so all I need to do is add that 4 over, which means x is going to equal 12. And that's it. Okay, let's try it again with example 2. Example 2 is going to be using more of those steps, like I said earlier, of isolating your variable. So what I can do first is I can actually add my 7 over, then I can divide by the 2, and then I'll just have, x on one side. So adding the 7 over would get me 11, so I have 2 natural log of 2x minus 1 equaling 11. Dividing by 2, I know that's not going to give me a whole number, but that's okay. The natural log of 2x minus 1 is equal to 11 over 2. All right. At this point, I want to rewrite this as an exponential function. Okay, so we know that the natural log has a base of e. It's just not written in. So I can rewrite this as e to the 11 over 2 power is going to equal my argument of 2x minus 1. Okay, I'm taking my base of e, raising it to that power of 11 over 2, and that's going to equal the argument of 2x minus 1. And so now I'm continuously still going to solve for that variable of x. So I can add the 1 over. Remember, e is a number. E is not a variable. So e to the 11 over 2 is a number. So I can add 1 to it. E to the 11 over 2 plus 1 is going to equal 2x. And then the last thing I need to do is just divide by 2. And yes, this is going to look ugly, but that is okay. E to the 11 over 2 plus 1 over 2. And that is my final answer because that is a number and that is the exact form. We want to leave it in exact form. If the direction said to round or estimate or something like that, then you could actually type in your calculator e to the 11 over 2 plus 1 divided by 2. Okay, that's it. That's your value of x. Okay, so remember, like I said earlier, we want to condense using our properties when possible and isolate the log expression when possible. If every term is a log with the same base, set your arguments equal to each other. Otherwise, rewrite it into the exponential form to solve. That's exactly what I did in example 2. Okay, I didn't have a log on the other side or a natural log on the other side of the equal sign, so I had to rewrite it in an exponential form and solve that way. Okay, remember whenever we solve any kind of equation or function, we always want to check our answers for extraneous solutions. So that's what we'll see in examples 3 and 4. So I want to apply all those properties that I've been talking about, condense when possible. If the logs have the same base, just set the arguments equal to each other. If not, we'll rewrite it as the exponential form and solve. So Example 3, I do notice that I have the log of x plus 2 plus the log of x minus 1 is equal to 1. I don't see the bases there, which means it's an understood base of 10. They have a common base. So they do have the common base. So that means I can condense. Because those logs are being added to each other, that means I'm going to multiply my arguments. That's the product property. So rewriting this, I would get log base 10, which I don't have to write. And that's my two arguments being multiplied together. So the x plus 2 times the x minus 1, and that's still going to equal 1. Okay. So at this point, if you want to go ahead and FOIL what's inside your parentheses, you are more than welcome to do that now. But there's no way that I can solve this because I don't have a log on either side. So I'm going to rewrite it into its exponential form. Remember, I have a base of 10. So this is saying my base of 10 raised to the first power is going to equal that argument of that x plus 2 times that x minus 1. And again, if you want to rewrite that, I'll do that in the next step. Okay, so let's simplify. 10 to the first power is just 10. X plus 2 times x minus 1 is going to give us x squared plus x minus 2. So I want to set this equal to 0 so I can solve that quadratic. This is something that we've done a lot throughout this year. Okay, you should know how to do this by now. So when I subtract that 10 over, I get 0 equals x squared plus x minus 12. So I need factors of negative 12 that add up to positive 1, and that is going to be x plus 4 and x minus 3, which means x is going to equal negative 4 and x is going to equal 3. But I need to check for extraneous solutions. X is in the argument of the original problem, so I'm going back right here because I'm going to plug in these two values of x's that I have. Like I said, x is in the argument of the equation. Well, if I plug in x as negative 4, I get the log of negative 2 plus the log of negative 5. The red flag should be going off in your brain right now. Your argument can't be negative. Your base can't be negative. The only thing that could be negative in these logarithmic functions and equations is your exponent, okay? Your base cannot be negative and your argument cannot be negative. Think about why. Hopefully you know this by now, but a logarithmic equation is the inverse of an exponential equation. Whenever we talked about exponential equations, we said that our base could not be negative. Remember, that would create this up, down, up, down, up, down with a bunch of holes on our graph. That's not possible. That's why our base cannot be negative. Our argument cannot be negative. So if I had to rewrite this, this would be log base b of y is equal to x, right? Why can our argument be negative? Well, if our base is not negative, I can't raise a positive number to any kind of power and get a negative answer. Okay, any positive number as my base raised to any kind of exponent, positive, negative, fraction, whole number, whatever, will never give me a negative number. That's why the argument cannot be negative. Okay, think about it in terms of inverses if you need to. So that means our answer is only x equals 3. X cannot be a negative number in this case because x is in the argument's position. Okay, so let's try this one more time. In example 4, we have log base 2 of x minus 3 equals 3 plus log base 2 of 3x plus 1. Well, good news that I see is that both of my logs have the same base. They both have a base of 2. So what I need to do is I need to get my x's on one side and everything else on the other side. So I need to subtract that log base 2 of 3x plus 1 to the left-hand side. So that's going to give me log base 2 of x minus 3 minus log base 2 of 3x plus 1 is equal to 3. Hopefully you know what's going to happen next. I have two logs with the same base that are being subtracted, so I can apply the quotient property. So I can divide that x minus 3 and that 3x plus 1. Log base 2 of x minus 3 divided by 3x plus 1 is still equal to 3. Okay, so because I don't have two logs or a log on either side, I need to rewrite this as an exponential function. So this is going to be base of 2 raised to the third power is equal to x minus 3 over 3x plus 1. 2 to the third power is 8. I'm just simplifying there. And so now I want to solve for x. So I want to get rid of my fraction on the right-hand side. So I will multiply both sides by the denominator. So that means I have 8 times 3x plus 1 equaling x minus 3. And this is just going to turn into a linear, so you know how to solve this. Distribute your 8. You'll get 24x plus 8 equals x minus 3. Getting your x's on one side and your numbers on the other side, I'm going to do 23x equals negative 11. And dividing, I get x to be negative 11 over 23. I need to check that into my original problem. Well, if I go to my original problem, where x is in the argument. If I plug in a negative x for my argument, negative 11 over 23 minus 3 is going to give me a negative number, which means I would have a negative argument, which means that cannot happen. So because that was my only value of x and it doesn't work, then that means no solution.